This is a video lecture for Math 140 for Tuesday, May 5th. This is the final video lecture of the year. This is part one of the video lecture. Today we're talking about ellipses, and ellipses are related to circles, but a little bit more complex than a circle. So what I want to do is start with something we learned with circles, and that's the factored form of the equation of a circle. X minus h squared plus y minus k squared equals r squared. So this is the equation of a circle with radius r and center hk. Now what we can do here is we can divide both sides of this equation by r squared. And that gives us an equation, x minus h squared over r squared plus y minus k squared over r squared. R squared divided by r squared is just 1. Okay, and this is called the standard form of the equation of a circle. And one thing we can note here is that r squared in the denominator in the x term here represents the horizontal distance from the center of the circle to the graph, and r squared in the denominator of the y term represents the vertical distance from the center of the circle to the graph. Okay. Now for a circle, both those distances are the same. Okay. But for other conic sections, such as an ellipse, these two different distances, the distance from the center of an ellipse to the graph, and the horizontal distance, and the vertical distance from the center of an ellipse to the graph, are different. And so what we can do is we can replace these r squareds with a squareds and b squareds. So we get something like x minus h squared over a squared plus y minus k squared over b squared equals 1. And it turns out this is the standard form, the standard equation of an ellipse, where a, and we'll come back to this, a is the horizontal distance from the center to graph, and b is the vertical distance from the center to the graph. Okay, I want to consider a specific example to illustrate this idea more clearly, that the two distances for an ellipse, the horizontal and vertical distances, are different. So let's first consider a circle that has a radius of 2 and a center of minus 1, 1. So let's consider that circle, and let's write the equation for this circle. So in the factored form, that equation is x minus 1 gives us a plus 1, x plus 1 squared plus y minus 1 squared equals the radius squared, which is 2 squared, which equals 4. Okay. What I'm going to do now is write this in the standard form. So I'm going to divide both sides by 4, or 2 squared, and I get this equation: x plus 1 over 2 squared, x plus 1 squared over 2 squared, plus y minus 1 squared over 2 squared equals 1. Now this is the standard form of the equation of this circle. And let's actually create a graph of this circle. I'm running out of room here. We'll create a compact little graph here. In fact, let me move this over here. I'm going to make this a little bit more space for a graph. Okay, let's erase this. Okay, let's create a graph of this circle. So we'll set up our coordinate axis system here. And we'll put some tick marks here, 1, 2, 3, 4, and so on. Okay, the center of our circle is at minus 1, 1, which is this point. And then a good way to create a graph of the circle is to create 4 points horizontally and vertically oriented from the center. And so we know our radius is 2, so the circle is going to be defined. If we move 2 over, we get a point here. If we move 2 up, we get a point there. If we move 2 left, we get a point there. If we move 2 down, we get a point there. And our circle will look something like this, if I can draw this correctly. This will not be perfect, but it's an okay circle there. And this is the graph of this circle. Okay, let me erase what's up top here. Okay, now the question is, what if we alter things a little bit? What if we were, as I talked about, in our more general form, this is a squared and this is b squared. In this case, a equals b, right? In this case, a equals b and they equal 2. But what if we had a different scenario where we make them different? In fact, let's consider the example where a equals 3 and b equals 2. Okay. Well, we can write the more general form of the standard form of that equation would be x, and let's suppose this shape has the same center as we have below. So x over x plus 1 squared over 3 squared plus y minus 1 squared over 2 squared equals 1. Now this is a little bit different than this equation. And recall that a is the horizontal distance from the center to the graph, and b is the vertical distance from the center to the graph. And so let's create a graph of this shape. The center is still minus 1, 1. The vertical distance, right, is still 2. But now the change is, I should have written this over here. So center is still minus 1, 1. Vertical distance is still equal to 2, but the horizontal distance is now 3. Okay, what does this shape look like? And let's create a rough graph of this shape. Okay, so here we go. We've got our coordinate axis system here. And we've got looking like this. We'll make our tick marks here. In fact, I could have drawn this on top of this graph here. Maybe I'll do that instead. Let's just draw this function on top of this graph. Why don't we just do that because we have the same coordinate axis system. I should have planned the board space out a little better here. But anyway, our center is still here. We still have the vertical distance being here, but now the horizontal distance is 3, so we have to go 3 to the right of the center and 3 to the left. And we get a shape that looks like this, if I may draw this correctly. This is very rough shape. Okay, so we get a shape like this. This applies to this graph. What do we have here? Well, what we have here, to put it in very simple language, is we have a stretched out circle, when I refer to it that way. And a stretched out circle is an ellipse. So we have an ellipse. So when a is not equal to b, we get an elliptical shape. And let me talk a little more generally about ellipses. So let me erase this. Introduce you guys to the wonderful world of ellipses. Okay, so an ellipse looks something like this. It's a stretched out circle. Has a center here. And there's some terminology we need to learn. Okay, there's one line, there's two axes of an ellipse. One axis is that axis, and then we have this axis. Okay. And actually, let me draw the vertical axis in red. Okay, so the blue axis is called the major axis. And it's basically the longest distance across the ellipse. And what's in red is called the minor axis. and it's the shortest distance across the ellipse. This board is vibrating a lot. Let me try it that way. And so this is the major axis. This is the minor axis. Now I also should mention that there's also what's called the semi-major and semi-minor axes. And the semi-major axis is half of the major axis. So this would be the semi-major axis. The semi-minor axis is half of the minor axis. So this distance would be the semi-minor axis. Now this is a case where A is greater than B, which we had in the last problem. You might actually wonder what happens when B is greater than A. So if B is greater than A, then your vertical distance is bigger than your horizontal distance. So if you have B greater than A, what happens is you get a vertically oriented ellipse. Okay, you get it. So you can have a horizontally oriented ellipse and a vertically oriented ellipse, depending on which is bigger, A or B. And let me summarize for you guys the general equation for an ellipse. And I already mentioned this equation, but let's write it out in its full glory. X minus h squared over a squared plus y minus k squared over b squared equals 1. And this is an ellipse that has a center, just like the circle has a center of hk. It has an a is the horizontal distance from the center to the graph, and b equals the vertical distance from the center to the graph. Okay, this is our equation of ellipse. This is an important equation. Let me box it. Okay, that's the theory behind ellipses. Again, ellipse is a type of conic section. It's similar to a circle. If you recall, if you have a right cone and you slice through it exactly horizontally, you get a circle. If you slice it at an angle, you'll get an ellipse. That's why these are called conic sections. And in the remaining parts of this video lecture, I'm going to do some example problems related to ellipses.